This session, we're going to be focusing on bioterials, how biomanufacturing and biodeconstruction improve our housing and reduce carbon. Before we get started, I want to say a huge thanks to one of our sponsors, Climate Adhesives. You know, homes and buildings are now continuously and growing under threat from both wind and seismic activity. And these adhesives can reduce that risk and prevent deadly damage and loss of life from occurring. During the new construction process, wood frames, homes, and buildings should be considering using climate adhesive to reduce that risk. You can head over to climateadhesive.com to learn a little bit more about this technology. All right, again, welcome everyone to Bioterials, how biomanufacturing and deconstruction improve our housing and reduce carbon. This session is brought to you by the GreenHome Institute. The GreenHome Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I will be your moderator. My name is Brett Little. I am the education manager here as part of our small but mighty team of 3. And as always, our courses are approved for multiple continuing education units, including, in this case, our certified GreenHome professional designation in the materials and place pillar. AIA Health, Welfare, and Safety may make it applicable to your state-based design or contractor license. All right, so with that, I am excited to have and introduce briefly our guest, Christopher Maurer here with Red House Studio. He is going to be introducing himself, his organization, and leading us through today's topic. So, Christopher, welcome, and please take it away.
Okay, thank you. Hopefully everyone can hear me. I'm glad to join you all today for the GreenHome Institute. This is Chris Maurer from Red House Studio. And I'm an architect based in Cleveland, Ohio, but we're working on several projects that kind of delve into the territory of material science and innovation, and even in some cases invention. We're going to look today at bioterials generally. First, you'll probably want me to define that, since it's a made-up word, and then how bioterials can actually replace a lot of existing building technologies in a way that actually, not only is more sustainable, but is actually regenerative. And so we'll look at biodeconstruction when it comes to blighted housing. Particularly, that's a big problem here for us in Cleveland. We have thousands of homes that are slated for demolition, hundreds torn down every month to kind of redevelop the urban fabric that we're in here. And we'll even take a trip off planet as we talk about these materials. So a lot of these materials are starting to become ready right now, but a lot of them are futuristic and still need quite a bit more research and development. But we're working with researchers at MIT and Stanford and NASA, and people a lot smarter than me to develop some of these capabilities, and we do see this as a bright future for architecture and technology. So I'll hopefully be able to advance my slides. I'm going to start actually off planet, and this is a computer rendering of a proposal or a project that we're working on with NASA. This is a bedroom on the planet Mars in the future, and a lot of the materials and objects that you see in this room will be able to be grown off planet. And you'll see some animations of that to kind of explain how that could possibly happen. But bioterials are touted for their ability to grow and in any location, really. If you give it the right atmosphere and climate for growth. So you could potentially take just small amounts of mass to a different remote location and have that expand into millions of tons potentially of matter if you have the right resources, which could include just solely water and carbon dioxide, as we'll propose here. on the Martian environment. But first, let's take a step back and define biomaterials. As I mentioned, that's a made-up word. A lot of people refer to the materials that I'm talking about as biomaterials, or just simply biomaterials. The reason why we've made this contraction here is because biomaterials can also refer to anything that works well with living materials. So that's titanium and plastics and things that are used in the medical industry, that are considered not to be hazardous to living materials. What we're talking about here are materials that are actually living, and they use the growth of organisms in their manufacture. That wouldn't include things like wood or bamboo that are grown and then harvested and then turned into different materials. Those are bio-based materials. Biomaterials actually have to use the growth of the organism in the manufacture, or what's being referred to as biomanufacturing, and biofabrication is another term that's kind of thrown around here. But we use the word biomaterials because it can be specifically defined as what you see there. There are a lot of different organisms that can do this type of biomanufacturing or biomaterial technology. Firstly, the plant kingdom, there are different kinds of algae, both from bacteria and from the plant kingdom, that can produce such thing as plastic alternatives. Bacteria are being looked at specifically to create a cementitious type of binding that can bind inorganic material together, and I'll show you an example of that in the next slide. Kingdom fungi is probably my favorite. You're going to hear a lot about mycotecture today, and mycology is the study of fungi. So what you see there in that picture is fungal mycelium, and that is basically the root-like branching hyphae of fungus. So it's actually the organism of the fungus, and most people think of the mushrooms as being a fungus, but that's actually more like the fruit of the fungal organism. It's the reproductive organ, or what generates spores, and of course is the edible part in most cases. There's a joke that every mushroom is edible at least once, but you probably want to eat the ones that are edible most of the time. There's also symbionts. So this would be combining certain of these kingdoms, and you'll see an example of that when we get to our Martian architecture later in the slide deck. But here are some practical examples of what I'm talking about. Up at the top left, you see some plastics that were made from the production of algae. The bacteria, there's a company called Biomason that is growing the bacteria to precipitate calcite. And that's kind of the same way that coral reef is formed. They make their structures out of the calcite precipitation of the organism. And here, Biomason is taking that precipitation and using it to cement together things like sand and stone, the same way that cement does that in concrete. Fungi, we're going to talk about buildings mostly here, because I'm an architect and we're doing a lot of building projects, but just wanted to show another application. Stella McCartney, fashion designer, working with a company called Milo, creating vegan leather alternatives, and very stylish and extremely high fashion products are coming online with companies like Milo, MycoWorks, and others that are producing materials for folks like Adidas and Hermès, and a lot of really fabulous companies. And then the symbiotes, again, we're going to get into that with the mycotecture off-planet project that we're doing for NASA, but that project actually utilizes the growth of algae as the substrate for growing mycelium on, and then that fungal mycelium becomes a very bioperformative material, and I'll try and explain what that is later too. But bioperformative really looks at things that living organisms can do that's dead organisms, or dead materials that we normally build with can't do, like self-healing, self-cleaning, and we'll see in here the ability to transform into becoming a radiation shield just by growing different chemicals. So I mentioned mycotecture and mycoterials, and all of those with the prefix myco are going to be referring to fungi, and again, usually using fungal mycelium. But there's a lot of different applications for this. Mostly, the biggest commercial application is actually to grow things like yeast, and then we're very familiar with beer and wine and different bread, different food stuff that has living organisms in the manufacture of the materials. But we're going to be looking at mycoterials that are for the built environment. And so that's kind of the definition of mycotecture. Here are a few commercially available materials now, or mostly commercially available. Most of these companies are actually in their research and development phase, and a standard customer can't buy them, but they're being used for applications. As I mentioned, Hermes and Adidas are looking at some of the leather materials. Ecovative is basically I think the biggest company and the initial pioneer into commercializing these materials, and they make packaging materials that are replacements for styrofoam. So where styrofoam, is meant to be used for a couple days or a couple months, and then the life cycle is thousands of years. This material, as soon as it's done, you can actually compost it, so it goes back to being useful straight away instead of taking up landfills and leaching toxic chemicals. So great alternative. And people have noted that, hey, coffins are kind of like that too. You really only need them for a little bit. You only see them for a little bit, and then it's best if they kind of go back to the earth the same way that the human body eventually will. And so there's a company called Loop that is working with Ecovative to make those materials. What you see there on the top right, that is our friend Ivan, who works with a company that we co-founded called MycoHab, that is turning encroacher bush, this invasive species in Namibia, into both food and housing by growing gourmet mushrooms and using the waste to make building materials. And we'll go into that in more detail in a bit. But speaking of mycotecture, I would say that these are probably the two biggest and most notable instances of mycotecture, and I would say probably the first one ever would be this one on the left, where Phil Ross, who's now become the co-founder of MycoWorks, that is making leather goods, did this art project in Dusseldorf, where they had living mycelium and mushroom blocks that were growing. That's reishi mushrooms you see there. Guests to this gallery were invited to harvest the mushrooms and actually use them as a tea. So he called this the tea house. And you can see there, it's technically an architectural structure. It's very temporary. It's an indoor structure. It's not weight supporting or anything like that. Not livable necessarily, but a beautiful sculpture and an example of what could come in the future. On the right there, similar example, it was a sculpture done at MoMA PS1 in 2014 as part of the Young Architects Forum. And this was done by David Benjamin, who's a professor at Columbia and an architect with a firm called Living. He worked with Ecovative to produce this exterior sculpture that was in the courtyard at PS1 for the summer of 2014. And those blocks there are made from mycelium that are growing on agricultural waste. So, one of the big things about this competition was that the materials would be ultimately compostable at the end of their life cycle. And so being made of agricultural waste and fungal mycelium, which is organic matter, all of this is biodegradable. And so this is one of my projects. We've started a company called MycoHab that, as I mentioned, is turning the encroacher bush of Namibia, which you see there in the background. That is, it looks like a very green environment, but that should look like a grassland. Those bushes that you see there are really causing desertification, so it's leading towards land depletion. And the government of Namibia wants to thin that bush. So they want to take it back to about 10% of what it is now. And so they're looking for economic outlets of that bush. Most people have found The only thing it's really good for is burning. So it's being turned into charcoal and fuel pellets and things like that. But we've found that you can actually not only use that to grow food in the form of gourmet mushrooms, but you can use the waste material from that to produce these blocks you see here and make structural buildings. So that building you're looking at there is the world's first structural mycelium building. It's a one bedroom apartment, if you will, or it's a one bedroom house. It has a bathroom, bedroom, and a small area for study and cooking, etc. We're working with partners, including Standard Bank and MIT, to develop this technology and looking to take this to build. If we use only 1% of the bush in Africa, we could build hundreds of thousands of homes, and that could be turned into, used to house the 500,000 people currently living in informal settlements. So for Standard Bank, who's the main sponsor of this, it's a very much CSI/ESG endeavor to create social investments. For us, it's ability to combat climate change and to create regenerative architecture. And as I mentioned, that is something where we're looking at the co-benefits of actually producing architecture are beneficial in comparison to normal building technology, where we see high carbon footprints and materials that are ultimately toxic and almost indisposable. These materials, as we debush, we're actually regenerating land. Every ton of material we make stores a ton of carbon dioxide by not letting it be burned or go to decay, by locking that plant matter up within these mycelium blocks. For long term, it's actually storing carbon dioxide, and so we see a total of 1 ton carbon storage per ton we make. Compare that to concrete, which emits a ton of carbon dioxide per ton made, and if you were to make the switch, you would have a 2-ton carbon offset by building with this material rather than solid concrete. And the reason for doing that is you all are probably aware, we're going to be building a lot in the next few decades. The world building population is predicted to double by 2060 from 2020. And to do that, that would be like adding a New York City of buildings every month for the next 40 years, according to the Gates Foundation. So, imagine every building in the world now and then double that by 2060. That's a lot of building. As I mentioned, concrete emits a ton of carbon dioxide for every ton it's produced. 4.4 billion tons of concrete are produced every year, so that's 4.4 gigatons of carbon dioxide released into the environment for just concrete. Concrete, steel, and aluminum alone account for 23% of the world's carbon emissions. Buildings generally are responsible for about 40% of the world's carbon emissions. But those 3 materials that are, not just for building, but for other manufacturing as well, equate to 23%, and 9.6 billion tons of that is directly attributable to the raw material resource extraction. So obviously we can, if we found circular resources, resources that didn't require material extraction, we could have a huge benefit already. And then if we look at carbon-based materials, building with carbon storing materials, then we can actually look at architecture and design as turning the dial the other direction on climate emissions, greenhouse gas emissions. This, to kind of explain how MycoHab works, this is our humble facility in Blackwater, Namibia, which is just a small distance from the capital, Windhoek, Namibia. You see all the bush in the background there going from left to right. We take that bush, it gets ground up into powder like sawdust. That sawdust is sterilized and then inoculated with mycelium, which again is the root-like branching hyphae of fungus. That mycelium grows over and through it and combines that dust into a composite material of plant and fungus. It fruits mushrooms. Again, that's the fruit of the organism. Those mushrooms are easily harvested, and then the waste material or the byproduct from growing is compacted into a brick like you see Ivan holding there. And we're currently working on the design and building of a biofabrication lab in Namibia that'll look like the building on the right be an arch structure. Again, the process in a nutshell: bush to mushroom farming. Mushrooms are harvested, taken to market. The byproduct is what's used to make the building material. We're not, a lot of people refer to this as a mushroom house. It's not made of mushrooms. The mushrooms are food, and food is sacred. Food goes to people or other living organisms to live and grow. The byproduct is what we're using to make the building materials with. And you see the press that we've made in Namibia that makes these blocks. The kind of impact model here is that we can do both humanitarian food and humanitarian housing in the place where we're constructing this. And then the exports can be sent all over the world, which are usually going to be these mushroom powders that can be sold as adaptogenic products that are vegan, conservationist, healthy, easy to export. All of that can be sold in the developed world at higher cost, that then can subsidize the humanitarian work that's doing there. So that's kind of the balance we're trying to strike. We have this regeneration in the architecture. We have the humanitarianism in the project, and then we have the goods that go to markets, and they kind of play off of each other. One, the mushroom sales subsidizes the humanitarian work, but the humanitarian work is kind of a bit of a marketing ploy, if you will, for the mushrooms that are sold. You can feel really good actually about buying a tea that builds homes in Africa when you compare it to the one next to it that doesn't do that. So the blocks that we're making are currently strong enough to build single-story structures, and here are a few examples of designs that we're working on. The one on the top right is the one that's been realized so far. We started simple, but we're moving to the one on the left, top left, directly now. And as we start to get bigger materials, such as slabs of material instead of blocks, we're looking at A-frame construction and different geometries that are easily built by slabs of material. And so there's some metrics on there, 6 megapascals and et cetera, but we find it's easier to demonstrate its strength just by looking at this unscientific yet we believe useful comparison of its impact resistance. On the left, you see the concrete block shattered to pieces. On the right, there's a small dent and a hairline fracture. If this was a seismic event that was causing that sort of damage, you would much rather be in the building made out of the right. We, as apples to apples as I believe this is, because there's one building material to another. We get a lot of pushback, and people say, "Oh, it's not fair." They're concrete apologists mostly. It's not fair because the block on the left was hollow. So last time I was in Namibia, which was last week, I had this reproduced with a solid block. As you can see, yes, there's some damage sustained to the myco block, but it's not the catastrophic damage that you see there. And this is, of course, because concrete is brittle, right? The myco block is able to resist the impact here. And although this is very unscientific, it is kind of illustrative of a seismic activity or lateral forces, or a crazy man with a sledgehammer trying to get into your building. So the things that we publish are going to be the laboratory tests, obviously, but this is not just fun to look at it. We do believe it's useful, and we justified breaking these materials for science. So again, the project MycoHab, I talked about the ability to store carbon dioxide. I should explain that a little bit. So the growth of fungus actually emits carbon dioxide. It's the growth of the bush that created the substrate for growing the mushrooms that actually drew down carbon during its life cycle. And the bush that goes into the process gets converted into the mycelium. The organic carbon stays within that equation there. Some of the carbon dioxide, or some carbon, is released as carbon dioxide. But after we get to the point where we've harvested the mushrooms and we've looked at the block and we detail how much organic carbon is left in there. There's about 43% organic carbon in these blocks. Now, if we take that 43 and we multiply that by the equation of carbon dioxide, CO2, over C, there's a 3.67 conversion factor of that carbon dioxide, or that organic carbon in there is worth 3.67 carbon dioxide units in the atmosphere. So that's how much the equation is drawn down. That's how much it's been condensed into the material. So we call that a carbon dioxide equivalency. And when we multiply out the tonnage here, we actually have about a 1.5 tons of carbon dioxide equivalency storage in the material for every ton we make. But I already told you it was only 1 to 1, right? So we're not getting a 1.5. The reason is that the process is to take this from the mushroom byproduct, the mushroom cultivation byproduct, to our building materials requires some carbon dioxide emission. So we have, presses that use electricity. We have ovens that use electricity, and there's some energy that is expended in here to make these materials. And so that's what brings it down to exactly 1 to 1 CO2 equivalency per ton or per unit of material that we make. Okay, so getting closer to home, we're going to Cleveland, Ohio now with a project we have called Biocycler. It uses a very similar process, but instead of turning bush into building materials and food, we're turning old houses into new houses. We're literally recycling houses in this project. I mentioned we have a problem here with blighted housing and thousands of houses being torn down. And they're mostly going to landfill. And in the US alone, 600 million tons of C&D waste, or construction and demolition waste, go to landfills every year. The organic material in that gets converted into greenhouse gases that eventually leach out. And there are even worse things in there that get leached into the water and the soil. So we're looking at the process here, not creating food in materials, but actually doing remediation in materials. And so the toxic elements that are, for whatever reason, purposely put into the built environment, things like lead in lead paint, petrochemicals and wood treatment, different paints and things like that, different glues and adhesives. A lot of those things can be remedied by the fungal digestion. And one of the things I want to mention about Biocycler is it's part of an environmental justice program, and you can't really explain environmental justice without understanding environmental injustice. So the justice part of that is everybody should have equal access to a clean environment. The injustice part of that is people don't. Communities of color have about 1.5 times more exposure to air pollution. Black children are disproportionately affected by lead poisoning, with over 2 times the average blood levels. Here in Cleveland, where I am, which is a majority Black city, our children have 4 times the national averages of lead poisoning, worse than Flint, Michigan, which was made famous last decade with the water crisis. The children aren't being poisoned by water here; they're being poisoned by the houses they live in. We have the blighted infrastructure here. There's lead paint in their environment, and that gets turned into dust. And when children are very young, if anyone's had a baby, they know that they touch everything and they put everything in their mouth. And so that happens in these homes, and the children are poisoned by their homes. When we talk about water lead poisoning versus environmental lead poisoning, the poisoning that happens in homes is about 80% of the lead poisoning we have in this country. The water is responsible for about 20%. So while it's important that we change out lead pipes, the more insidious vector is the homes that we have here, the crumbling infrastructure that children live in. So I mentioned we might be able to do something with our fungi, right? So we take this C&D waste, and similar to what we're doing in Africa, we inoculate it with some mycelium. But instead of making food out of that, which could potentially bioaccumulate some of those poisons, we're just going to grow the mycelium. We're not going to grow the mushrooms. We're going to pre-filter the materials, and the the fungi are going to remediate the new materials, and we can create new housing out of that. So the fungi can do this in a couple different ways. When we have very large molecule chains, things like petrochemicals, or as we're showing here, polycyclic aromatic hydrocarbons, which are very tightly bonded petrochemical byproducts that are hard to break down. The fungi can do that rather easily, actually. The reason is that these are hydrocarbons from millions of years ago. They used to be trees, right? And so fungi likes to break down those hydrocarbons, and they can do that and produce new materials. Some CO2 is made in the process, but the main thing is the poison has been eradicated. So these long molecule chains are split up into smaller molecule chains of monomers rather than polymers, and they are safe in the environment. Now, heavy metals are much harder to deal with, and a different tact is taken here. So whereas the large molecules need broken down into smaller molecules, when you have elemental toxins, you can't break them down any further. You have to do the opposite. You have to actually chelate them or pair them with longer molecule chains that make them biologically unavailable. So the first thing we do is obviously try to filter out as much of the heavy metals as possible. But the second thing that we would do is whatever's left over then becomes neutralized by this biochelation that can pass through the body without causing lead poisoning. If you've ever known anyone to have lead poisoning, they probably had chelation therapy, and that are chemicals that go into the body. They latch onto the heavy metals, and they're safely passed through the urinary tract instead of staying in the bloodstream and getting absorbed into bones and causing long-term developmental damage. So this is kind of a pre-chelation therapy, if you will. Obviously, the filtration is the most important part of that, but when you're still left with parts per million or even parts per billion, you want to neutralize that as much as possible. And that's not only during its life cycle so that it's safe in its use. This actually remediates it so that when it is eventually landfilled or disposed of, that material won't leach back into the environment, as what happens mostly with demolition material taken to landfills. It poisons the water supply nearby by leaching. So we've ran several tests on this, including EPA supported toxic leaching characterization procedures and others. We started out with about a 30% reduction, and we said we can do better than that. The last test that we ran had a greater than 90% reduction in the lead levels in just 5 days, using this passive bioremediation. That wasn't including any kind of filtration at all. So this was just seeing how effective we could get with the bioremediation technology. We believe we can get this to 100%, and so we continue to working on that with researchers at Case Western Reserve, at Johns Hopkins, and other major institutions looking at community health. The goal for this, you saw some blocks before, but we want to get into the sector that's relative to cross-laminated timber. This being a AIA supported program. I think probably folks know what that is, but it's taking lumber and laminating that in different directions, and you can make slabs of materials or columns very easily, and you can actually replace concrete superstructure in high-rise buildings now. The code is starting to allow. We're really excited about CLT or mass timber technology, as it's called, because it stores carbon, but the unintended but not unforeseeable consequences of a proliferation of that is going to lead to more deforestation. So we want to get into that market as soon as possible and show this can be done with circular resources, with waste resources, and not requiring virgin lumber, using the same techniques. We can get compression strengths of 26 megapascals. We've gotten bending strengths of over 200 megapascals. So these can be used in similar applications to cross-laminated timber. And you see, just by aggregating these materials and using ideally biodegradable structural glues, you can get very, very strong materials and get all kinds of different market sectors through this, through prefabrication and different building technologies. So that takes us to space. So we started on space, and we're gonna, I think, end here. In both of the previous projects, you saw how we took waste resources and we used fungi to turn them into something useful. Here, you're actually going to see very similar, but obviously there's no waste biomass on Mars or the moon. So what waste resource are we looking at? Space radiation, and I'll come back to that as I talk about this. But this is a project we're doing for NASA through the NIAC program. That's NASA Innovative Advanced Concepts. We've made it through 2 phases of their project. We've just been invited and applied for the 3rd phase. The 3rd phase is very difficult to get into, but we're optimistic because we've seen a lot of support from the committees, and I think I'll show you here even the administrator. So the gentleman on the left is our colleague and researcher, Dr. Jim Head at Brown University. He helped train Apollo astronauts, and he's our planetary scientist on this project. And the gentleman on the right is Senator Bill Nelson, who is the current administrator or the big boss at NASA. And they're demonstrating one of the materials that we've made. I have another one just like it right here, if you all can see me on screen, but I doubt you'll be able to hear this, but when I hit on that, it sounds a lot like wood, and it basically is a woody type material that can be made from the combination of, again, plant and fungi in this application. The reason for this became firstly exciting for NASA was the ability to get small amounts of mass, even grams of material, to a new destination and turn it into potentially millions of tons at destination just by adding things like water and gases and other nutrients required to do that. It's very expensive to get a pound of material, so that's a can of soda, to the moon and to Mars. Could be as much or even more than $100,000 and $1 million, respectively. So here's an animation of how that might happen. We have, a standard inflatable structure here. So these are already being proposed all over the place to go into lava tubes, and they can serve as habitat that at least encloses air, but has very little protection because you basically got fabric there, and that can protect from most things other than radiation or heat. So what we have here is bioreactors that are in the shell, and you see as they're filling up with water, the preceded organisms turn into algal colonies. Here with the green mat you see there, or the green moss, that's a type of cyanobacteria, and then that serves as a substrate for growing the mycelium on it. And then these become hard materials that replace the soft shell of an inflatable. And those materials are bioperformative in several ways, as we'll discuss here momentarily. Here's a section through the building, so you can see from left to right that transitioning from being the algal colonies to the fungal algal composite materials. There's different substrates that are possible. For the moon, we're mostly looking at hydrogels because we won't be able to take carbon dioxide, or we won't have carbon dioxide to harvest at planet, so growing the algal substrate will be difficult. So we're going to start with hydrogels and inoculate them directly with the mycelium to produce some hydrogels or aerogels, as I'll show you later. But the autotrophs, things like kelp, Chaetomorpha, Chlorellus, spirulina, these are mostly aquatic plants or bacteria, and they are served as good substrates. So there, if you have a carbon dioxide source like you do on Mars, then you would be able to grow those autotrophs firstly to be the substrate for growing that and need even less resources. And of course, Mars is further away, so every pound counts there. We're looking at various mycelium species, and we've actually found one very recently that is extremely radiation attenuating. And I'll talk about how that happens in future slides. But first to the architecture. Basically, the outer shell of this is a series of bioreactors that we're calling cells because they kind of mimic living cells in an organism. They're linked together in a way that can form kind of a structural shell to the building by just adding them together. The materials can kind of keep that orthogonal shape, even though it's inflatables, by using drop stitch that connects the top and bottom with some very light stitching, and then that stitching in turn becomes a reinforcement for the bioterial that's created using this. There's different mixes of regolith and mycelium that can be used, but the purely organic bioshells will be the most effective for both thermal insulation and the radiation resisting. And I guess while we're looking at this image, it would be a good time to explain, while here on Earth, we're mostly concerned with gravity loads and weather, when we get off planet in areas without atmosphere, most of the structural forces are actually going to be outwards because we're in a pressurized vessel. So that's why inflatables are very useful, because they have the ability to take the tensile loads that comes from being in a pressurized vessel. So the structural ability of this design is mostly taken by those fabrics, which can include Vectran or Kevlar, which have 3 times the tensile strength of steel. And then the other things that you really need to guard against in space environments is going to be the radiation and the thermal swing. So on the moon, you go from about -200°C to a +200°C from day to night, and those days are 14 days long, and the nights are 14 days long. So they're really hard to withstand. So you need very good insulation, and you need radiation protection, because on the surface of the moon, you're not protected by the radiation shield of the Earth's atmosphere and the magnetosphere. This is just an example of how easy it is to grow some of these organisms. Chaetomorpha is often used as a scrubbing agent for nitrogen in fish tanks. And basically, it's, it could be used afterwards, but it's mostly just kind of a scrubbing thing. And when you look at the chemicals that are needed to grow this, everything there sometimes are in parts per thousand to the water, but mostly parts per million, which means very small amounts of these materials that you may have to take with you, paired with water, becomes a huge resource for growing these materials. This is kind of a complex system that looks at actually using the algal generation as part of a life support system. So it can scrub carbon dioxide from humans breathing. It can scrub human waste from toilets and things like that. Can actually convert that into useful materials. That's probably further down the road. Most of these buildings were inventing to be fully grown before human beings go to the destination. When you compare them side by side with a lot of what's called ISRU, or in situ resource utilization materials, they compare very well, even in the material characterization department when it comes to strength of material. But as I mentioned, mostly the thing you need is tensile strength, and that is taken up by the fabrics. In this case, what you really need is something that can block from radiation, and something that can has a very high R value. So here you see a citation that shows that within 30 centimeters of this, you can block from radiation, but it will take up to 300 centimeters, or 3 meters, so 10 feet of other materials are needed, things like regolith or sintered basalt. And once you're 10 meters underground, you're basically living underground, in my opinion. So we've recently done some tests. Well, let me explain radiotropism first, and that's the ability of several fungal species to harvest usable energy from forms of ionizing radiation, such as gamma. So space radiation are things like gamma rays, X-rays, high UV rays that get filtered out by our magnetosphere and atmosphere. There's also particle radiation, and that's the more difficult one to deal with. But most species that have a high melanin content on it are shown to be radiosynthetic or radiotropic, which means they have this ability to, much like photosynthesis, where plants convert sunlight into biomass, the fungi are actually able to take this high energy radiation and turn it into biomass, so that we can use this biggest liability in space travel as a resource for making the materials. So we produced a lot of samples using melanin-rich fungi. Melanin, of course, exists in all 5 kingdoms of life and is what human beings use to protect themselves from UV radiation. The fungi are able to do that at a much higher level. So we made these materials and we sent them into space. Here they are before they went to space. Here they are in the space station inside. And then here they are outside of the space station, where you get exposure to things like space radiation and very little atmosphere with atomic oxygen, which can be very dangerous too. If you look at that light bar on the left, it took me a second to realize that was the Earth's atmosphere that we're looking at there. So we're in low Earth orbit. We're very high above the Earth, and these materials are getting bombarded by space radiation. When they came back, very slight degradation to them, but a lot of materials don't come back. They get totally disintegrated in that environment. So superficial damage is not too bad. We actually found some micrometeoroids embedded in these. So we know that they can stop those as well, which are kind of like tiny bullets that fly through space. The result, we're still doing a lot of testing on this, but a recent test of a sample we took to Brookhaven National Lab stopped more than 99% of the proton dosage one could expect on a Mars mission, or sorry, a lunar mission, more than 99% with just 8 centimeters of material. So look at before, when we said 30 centimeters was our goal, and the competitor was 300 centimeters. These materials are very effective of stopping proton radiation. So there's all different kinds you have to stop from. Beta, alpha, a lot of those things can be stopped, but with just even a piece of paper or a little bit of water. But the proton radiation is the really tough one to deal with, and that's where these materials seem to be extremely effective. This is animation. I'll try and skip over that. I'll try and skip to towards the end of that, just to show that it's not just the architecture that can be produced this way. When we started with that first slide, I said a lot of the things in the room could be produced that way. So you saw that building grow, right? It filled with a liquid, and that liquid then turned into a mycelium material. The furniture could as well do that. So imagine, not unlike an air mattress, but something that could fill with a material that then at the end of the day becomes a very spongy or cushiony material, rather than a hard material like you saw here, or a liquid material. It becomes somewhere in between, like almost like a gel. And here you see some of the gels that we have made, and I have this one in a dish of water, so you can see the consistency is very much like water. It's actually 99% water, and then it has a little bit of a hydrogel called agar, along with, in this case, it's pure melanin that we mixed in there to do some experiments with. On the top right, you see one that's mixed with iron oxide, which is very prevalent on the Martian surface. It kind of looks like a box of chocolates, but it's also a really great way to protect from radiation. Here are some aerogels that are made with a very similar process. First, you make the hydrogel, and then you put that in a freeze dryer, and then you get a material like this that is 99% air. So that tells you about how light this can become. So that material there has about 1% solid mass. The rest of it is, that came from the hydrogel and the melanin that was mixed in with it. But the rest of that is air. It makes it a very incredible thermal insulation. And then the melanin that's infused with that makes it a very good, effective radiation shield. So these materials could be made potentially in situ or off planet, that are extremely good insulators and extremely good radiation attenuators. That leads to where the architect comes back into the picture, and we have some designs here. We call this the Red House Black series, and these could be filled with those hydrogels that can either be continued as hydrogels or turn into the aerogels, but both being very effective radiation shields. And so when you're off planet, and you're spending 8 hours in a bed, it makes a lot of sense to shield that doubly. So redouble the efforts to shield there. Also furniture, relaxation time, work time. You see a chair there, but all of these things along the top row could be useful on the Martian or lunar surface. Along the bottom there, you see an example of a bed that kind of fills around our space traveler there. This could be useful for low Earth orbit, and we're potentially working with a group that's building a space station that will have hotels, hotel rooms in addition to the laboratories. And we imagine a comfortable environment that keeps you from floating out of bed. So this thing kind of wraps around you almost like hugs you in place like a sleeping bag. Currently, they use sleeping bags tied to the wall, and we don't think that behooves a 5-star hotel. So we're developing some furniture that addresses that. Here's another interesting thing that happens with the hydrogels. If you dehumidify the environment and humidify it again, they can kind of grow and shrink. So that's useful for light packing. And then when you get to the destination, you can actually grow that material again. This is in a planetary simulator in Canada that actually mimics space radiation, space temperature, space atmospheres. So what's happening there is it's going from a atmospheric pressure to a lunar pressure, which is basically a vacuum, and that's why they're growing and shrinking. So another bioperformative aspect of the materials. And I think I'll just quickly flip through these because I want to get to questions, obviously. But this is one of the building proposed, which is kind of the main house. This is a pup tent kind of concept that can grow very quickly using the gels. They would mix with the water found at any destination along the way. But if you had a several-day mission, you might want to bring a tent with you. And so that's an example there. This is a little more futuristic concept that looks at having a larger base, and that this could have laboratories and residences and everything embedded within it. The ability to expand these things makes it so you can take a very small package and grow it into almost like a small town or a village with one basically payload. Rover garages, another thing on the table, and the left there you see a models that we've been mocking up. I have I think a animation of that right here with a musical break for everybody. But you see, I have a hand actuated pump to the right there, starting to fill this thing up. This is just made out of silicone. It's kind of a very dumb model of what's happening here, but this starts to take shape, and the space underneath it is actually empty. So the whole building is curving upwards now, and there's empty space below it. If you look to the left, you can kind of see that. So it's not that this thing is filling up like a balloon, but the outer shell of this is filling up, and that serves as an example of what could be filled with these gels that then turn into mycotecture. Here's another brilliant piece of stagecraft. You see the Earthrise in the background here, and then again a silicone model that is inflated by hand pump. And then you see this one is better illustrative of the empty space below, where we see our space explorer. And you can see it's inflating even a little more in there. So that brings us to our last slide, and why I am advocating for bioterials, or why bio generally, is because bio can store carbon, bio can perform, it can heal, it can clean, it can detect. I didn't talk about that, but there's ability for these organisms to actually detect pathogens in the environment. So imagine a sprinkler system for diseases rather than smoke. They can remediate, as you saw with the biocycler, and they can shield, as you see with the space radiation protection we're talking about. They can self-sustain, so being able to grow or add on, or just by adding different nutrients or conditions, they can repair themselves. It's renewable. We're always going to have waste, so circular resources are generally pretty renewable. And yeah, bio is circular. So there's a lot of benefits to bioterials that I think is going to lead us into a revolution, a bioterial revolution that will kind of change the way architecture and building happens. And ideally, that will be for a regenerative force rather than a destructive force. And I'd love to turn it over to questions. I see there's a few in the chat, but I will close my screen and pay more attention to that.
Yeah, hey, thanks, Christopher. And real quick before we get into those questions, just a reminder that this session is being recorded. It's hosted up on our YouTube channel, so you can check back in the next couple days and see the recording if you want to rewatch it, or go there now, hit subscribe, and get an instant update. For those of you watching this in the future, not right now, make sure to take your quiz with an 80% passing rate to receive your continuing ed certificate. And for those of you watching this today, make sure to take that survey that pops up, and then check your spam over the next couple days for certs at gutenbergcerts.com to receive your continuing ed. And as always, a huge thanks to our volunteers, our executive director, Jose Reyna, our board of directors, nearly 300 members, and all of our sponsors who are helping you build healthier, more sustainable, and greener homes. Thank you for their support. So, I always, Christopher, I always think about how we, have to build better in space to survive there, and bringing that technology back to Earth, and how even air tightness, if I think about it, obviously that's key. And we're still struggling with something like that here. So it's really inspiring to sort of, kind of look across how we need to get where, we could be building off planet, and how maybe some of those ideas come back here to help us build better. And I think obviously some people are more inspired about building right or going into space. And so seeing that technology come back, and especially as it's related to bio-based technologies. So I think one of the questions I had, and another guest, the way they asked the question was thermal conductivity. They put a formula, but R value, right? A lot of us are thinking R value, we're thinking U value. What are these, at least on Earth, if you're suggesting we put our, these blocks in our buildings, what is the R value of these?
Yeah, very similar to when we have the compacted material. So the material like this, it's similar to cross-laminated timber. So it's going to be okay, but not fantastic. But when you have the material like you see behind me here that is uncompacted, the R values are very similar to fiberglass bat insulation. So I think you get like an R3 per inch of material. So it's a very good insulation in the fact that there's a lot of air in between the particles. So this dries out, there's a lot of air pockets, and then the transition between conductivity and convection between those is what makes that a great insulator. When it comes to aerogels, those are the best insulators there are, because it's so porous, and it has so many of those connections between the conduction that goes through the solid and the convection that goes through the gas, and then on and on and on to get through the material. That's what makes aerogels extremely attractive and the best insulators on the planet or off the planet, actually.
Right.
Yeah.
So would you foresee the aerogels being a possible, insulating material here?
I do. Yeah, I do. And I think it is being used in certain instances, very kind of high-end instances, but there are some scenarios where the aerogels are put in between glass panels, or they're put in between even plastic panels and inflatables. And so I think a good example of the type of inflatable that we're kind of mimicking with our fenestration is the soap bubble building at the Beijing Olympics that had these basically all of these windows that were inflated kind of like a lens a scenario. That some domes are being made this way now, where they take inflatable materials, and then they fill the cavity in between those with air. So if you were to fill that with an aerogel, not only would you still be able to translucently transmit light, but you would be able to insulate at the same time, and insulate at levels that we're talking about with space temperatures, a delta of room temperature to -70 C on on the exterior. So huge amounts of potential heat transfer. So yeah, I think we are proposing some everyday products for this. It's going to really involve getting the cost down for the aerogel creation. I think that's the market stop right now. And that's why it only exists in high-end products. But it's getting into fashion now. So there's a lot of jackets claim to be aerogel filled. I think they contain some aerogels. They're not technically filled, but the kind of aerogel you get in the silica packets that keep things dry, those are used now in fashion in insulating coats and things like that.
Mhm.
So yeah, I think that there needs to be a bit of an increase in the or decrease in the cost of production, but I believe that that will be a material we use for insulation more and more.
So I would assume then in colder climates, you're talking about really two different types of materials, because the block is structural, right? But it's not a great insulator. So maybe one
Yeah.
that's structural, one that's insulation. What are the thoughts? Any thoughts on that?
Yeah, absolutely. And when we first started looking at this, we were thinking, I did a building section, and you got your exterior material, then you got your weather barrier, then you got your insulation, you got your stud kind of in the same cavity. And it's like, okay, we could switch that insulation with something like this. And there are companies that are trying to commercialize mycelium insulation. And then your studs you could do a different way, a little bit more like this, or like this. And then you put all those things together, and it's like, wait a minute, let's just make the wall, thicker. Let's
Yeah.
have the structure, kind of, or the insulation dictate things, and then you got more, material maybe than you need, but the material has co-benefits of actually storing carbon dioxide. So it's not like I'm afraid of wasting material here. The more material we use, the better it is for the environment. So, for once, it's like, okay, let's use a lot. And I feel the same way around like straw bale construction. That's a very cool way of building, where you get these really thick walls, a very cheap material. You can get that thickness pretty simply, but that goes to great insulation and the structure at the same time. So kind of a similar ethos there. But if we're talking about extreme temperatures, yes, you would have to have that extra insulation, and the aerogels would be fantastic. But you could also, depending on how green you're trying to be, you could have extra polyiso, or different types of rigid that could be involved with that. But we try and make everything either biodegradable or recyclable. So
Right.
our exterior shell is always going to be something that we need to, we're not going to use these materials for the shell of a building that's exposed to hurricanes and things like that. We would want, say, metal for that. Or we have very high UV. We have, not inconsequential storms in Namibia. So we have a very large roof over it, and we've covered the outside with like a mud plaster for the first building we've done. So that there's different ways of doing that. But if you can make the materials mostly either biodegradable or recyclable, then I think you got a green building.
Mm-hmm. And are these materials more probably permeable, as far as like not trapping moisture, but just allowing it to pass through?
Yeah, and similar to wood again
Yeah.
in that regard. But yeah, if we have left a lot of the blocks out in the environment in Namibia, and they wear over time. It weathers.
Yeah.
Weather is probably a better way to describe it than decaying. So it's
Right.
kind of like rammed earth construction, where you make it, a couple extra inches thick, and after 20 years, if it's shrunk, a couple inches, it's weathered that much in a couple years, you still have, a really damn good wall.
Right. Right.
Yeah.
Right. Um,
But that said, we do protect it as much as possible, and we don't plan to leave these materials out, but if they do somehow get exposed, if the plaster breaks away, or somebody comes and steals your steel corrugated siding, then your building's going to be good for decades. even potentially century, depending on how thick it is, regardless.
Yeah. Um, clearly you showed at least the unscientific test, and you're doing scientific tests of
Yeah.
smashing the concrete, smashing the block. I'm kind of thinking, seismic resistance, probably wind resistance there come to mind. What about fire or flood resistance in these applications?
Yeah, we've done some testing on that. The larger testing at the building assembly level, we've yet to do. But the what's really interesting about the mycotecture, even though they're made of wood originally, the mycelium that kind of coats all of that is self-extinguishing, and is fire resistant. So you get, if you continue to hold a flame to the thing behind me, you'll eventually burn through the other side. But if you
Right.
try and light it on fire and then walk away, it's going to put itself out. And then add to that the blocks that we're doing in Namibia are over 8 inches thick. They're 25 centimeters. So that's a lot like mass timber or cross-laminated timber, where it's going to take several hours to burn through that. So you got a 3-hour, 4-hour wall, just by the mass of that product in itself. So as far as fire spread, there's good news there because of the thickness of the material. As far as fire development, it's self-extinguishing. But as this material burns, it is going to smoke a lot. So you still have that smoke development that becomes very dangerous for the people in the room that's burning. But protect your neighbors, or the next room over are protected from this fire passability.
Right. And in the event of these buildings being exposed to flood, are they, what is the,
Yeah, so they're hygroscopic, so they're able to breathe the moisture. So, there'll be some damage from that, but if you're able to dry them out, you're a lot better off than you are with standard construction, because
right.
we'll just be able to wick that moisture out, as long as it's not submerged for a very long time. But even if it is, we've submerged material for quite a while, and it just kind of weathers rather than rots. But yeah, if you can dry it out quickly, enable the air or the moisture to migrate, no problems there. Gypsum board and other things tend to mold. These materials, if you dry them out, they ironically don't mold as much,
Yeah.
even though they were specifically designed to allow fungus to grow on them.
So someone here was mentioning, they have this large field of invasive buckthorn shrubs across the street, and so expanding on the question, like, if we have these invasive woody fields somewhere, anywhere, are these then great materials for this use, or?
Oh, yeah, I think absolutely. When we look, we've started in Namibia. There's about 400 million tons of bush that needs to be cleared there. If you look at America, the resource that comes to mind is, straw that's a byproduct of growing grains. We have, hundreds of millions of tons of that here in Asia. Rice straw, millions of tons, hundreds of millions of tons. Bagasse, which is the waste from sugarcane farming, again, hundreds of millions of tons. So there's a lot of biomass that is going to waste, and a lot of it is being burned. And so that just takes all the carbon dioxide that's been drawn down from the environment, puts it right back into the environment. If you're able to convert any of these invasive species, or this straw or this bagasse, into building materials, you can potentially lock that away for decades, even centuries. And kind of store that carbon dioxide instead of letting it go into the environment through other processes.
Switching to the remediation, well, the question here was, do you have any studies or published research on what you've been able to accomplish with that?
Most of the data that I've shown you today is our internal studies. We're working on peer-reviewed work right now. That's the funding that we're looking for. You know, a lot of times I joke that, you know, I live here in Cleveland, I can get funded on the moon and I can get funded in Africa, but you know, when it comes to helping people here in Cleveland, we just can't find the benefactors for that. But we
Yeah.
have done these studies with you know, very reputable collaborators, including research scientists at Johns Hopkins University and Case Western Reserve University. But we need to get the funding to run the, you know, the trials that can then be peer reviewed and you know, put out there as data. But yeah, what I showed you today was internal experiments. We work with different laboratories, including Galbraith, I think is a laboratory in Tennessee that we've used to run what are called toxic characterization leaching procedure tests. And that's the EPA test for understanding what comes out of the leachate of something that's landfilled. So that's where some of that data came from. And then the most recent test at Case Western Reserve University was done by environmental and environmental scientists and civil engineers there. So, you know, very rigorous testing, but yeah, not published or peer reviewed at this point.
Yeah.
It's in fact a little proprietary, and I you know, gave you kind of the inside look there, but yeah, suffice it to say that is our goal, is to be able to remediate 100% of lead in the worst home here in Cleveland or anywhere, you know. So you know, there's not going to be, you know, tons and tons of lead dust, but there is going to be a lot of lead paint, different lead in different products that can be there. So you know, we're going to set a control for like the worst possible environment and try and get that down to 100% remediation is our goal.
And just to be clear, is this for homes that are slated to be, you know, demoed, or is this also for existing homes where you're going in and doing a lead repair project, or both?
Both. So we would start with the, you know, the ones that are slated for demolition. So we would want to keep that out of the landfill. But as the process scales and we prove the technology over years and years of doing this, what we would like to do is try to get a public mandate to say, let's stop poisoning people. Let's replace all the homes, as they're doing with the lead pipes now, right? With the Inflation Reduction Act and other things. Let's set a mandate to be able to take anybody that's living in a deadly toxic environment. Their children are becoming developmentally delayed from their environment, and let's have a mandate for cleaning that up, recycling that house, and actually having a clean house put in its stead. And so, you know, with the matter of you know, say 6 months to a year, recycling a very small house seems doable. And if you have enough of those going on at the same time, people can kind of move around. But our goal would be safe homes for everyone. And there's 30 million homes in America that have dangerous levels of lead paint within them. So, you know, a lot of work to be done. But, you know, we don't think we're going to do it all. But, you know, if we come up with this process and we start to license that to people that do have capacity like that, or lots of people that have capacity, then you can start to address that problem.
Yeah. And I think about, you know, demolition, and it's so hard to convince, you know, any kind of demo program to consider deconstruction over demolition.
Right.
And it almost seems like, I mean, how much, so we're just trying to you know, convince people to do deconstruction. It's such beating your head against the wall. Then you say, well, do deconstruction with this in it. How much more would this add to the effort of doing a normal deconstruction process, or would it help?
I think it would help. So I think it's enticing because, you know, you can convince somebody to separate out copper, right? Why? Because they can sell that. If you convince them, or you do it yourself in a way that separates out all the organics and allows them to go through this, you know, fungal digestion, and you're getting paid for that. You know, I mentioned 30 million homes. If you get $20,000 a piece for those, you're $600 billion or so, right? So that's a huge market, that you know, brand new market that could come online to do those type of things. And so if you could get paid for those ecosystem services, then that's the enticement. And that's this scenario with copper, and the scenario with the recyclables. There are some folks that already sort the organics for turning into mulch. And yeah, I'd argue that's pretty dangerous because you don't know if there are these contaminants. Most of the time, you don't know if there's these contaminants in there, and then you're just putting that into potentially a mulch bed that turns into a vegetable garden, and then people are eating from that. So that becomes dangerous to do without knowing all the facts. Here we
Yeah.
just assume the worst, right? And then we kind of go from there. And so we're going to remediate as we recycle in every scenario.
Yeah, 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 kind of a precautionary
Yeah.
principle thing. Um, and then real quick to, I was listening to everything you were saying on space, and clearly you had mentioned that we have different situations, right? We've got weather and gravity on Earth. You mentioned we've got in
Mhm.
space, you've got the swinging temperatures and radiation. But just out of everything you were going through, it was kind of clicking on me, is some of that applicable to maybe quick emergency shelter applications? Do you have anything like that on Earth where that's needed?
Yeah, absolutely. So the biocycler is also geared for that type of project, because one of the worst, the toughest thing is to get relief aid in with all the debris, right? So if you have
Right.
folks that are going through getting the debris out of the way, that debris then becomes, not only the organic debris from the homes, but the fallen trees and all of that becomes a great substrate for doing these types of processes. The inorganics can be recycled in other ways that I won't go into, but it has to do with the bacteria. But again, you're creating an enticement for getting that debris out of the way because you can have an economic outlet for the debris itself. And so that's one scenario. The other one is as you were noting, that the deployability of the Martian habitat is something that could be very useful in hot or cold climates. We have a proposal underway that's looking at doing a very simplified version of that to do cooling centers. So, imagine an inflatable that goes up, it's air supported, it's being pumped with ideally, solar powered air conditioning. And so that's what's holding the building up, but you still want to insulate that really good so you don't lose all that energy. And then you would have a mycelium dome over it that would be more like this material, very fluffy, lightweight material. And then at the end of the season, when it starts cooling down, you can deflate this, and then the material that was there gets composted into a community garden right where the habitat was, or where the cooling station was. So that could be useful in very cold climates, exploration into Greenland. We looked at Antarctica. The biomaterial isn't really seen as a advantage there because of the laws there. But cold environments like North Slope of Alaska or Greenland, those type of areas. Hot environments, again, like we're being able to use this as cooling stations, or humanitarian relief that could continue to be a very cool environment.
Yeah.
So the building that we did in Namibia is the only building on the whole campus we have there that isn't air conditioned. And then the hottest days of the summer, it's the best one to be in, just because the insulation value, the big roof, the breeze that goes through there. So very passive techniques. That makes it extremely good with it, thermal mass and everything that's involved with that as well.
Yeah. Well, we're at the end here, and I really appreciate your time and going through all of this with us today, Christopher. Just real quick, where can people go to contact you or learn more or reach out?
Okay, yeah, look on Instagram for Red House Architecture, Red House Studio Architecture. It's pretty long. I'm not on Twitter much, but that's Red House Arc. Our website is redhousearchitecture.org. And my email address is chris@redhousestudio.net. So they're all different. Unfortunately, we screwed that up, but yeah, look for me on LinkedIn or Instagram mostly, or online, please.
Yeah, well, Christopher, I really appreciate your time. Thanks for going through all this with us, and thank you all for joining us. We'll catch you on our session here next week. So take care, everyone, and be well. Thank you.
Thanks a lot.